In today's lecture, we'll be talking about ordered sets and upper bounds, but before we continue, I want to talk quickly about some of the things we went over in our last video, which were about fields. And I spoke briefly about the field axioms A1 through A4, and if you remember, they look something like this, where a field is a set with two distinct elements, 0 and 1, two distinct binary relations, plus and multiplication, and they follow a certain set of axioms. So the commutativity, associativity, the existence of an identity, and the existence of inverses for addition and multiplication. And I wanted to make the point that everything we do in algebra and all the seemingly intuitive formulas that we come up with to do our algebraic expressions are derived from these axioms. And I want to give you an example here. So take, for example, the very simple statement x plus y equals x plus z, therefore y is equal to z. This is very intuitive and makes sense if you've ever taken a basic algebra course, but the reason this is because of these axioms and the definitions of these axioms. So if we want to prove this is true, we can do so by simply stating this. Negative x plus y is equal to negative x plus z. Okay? This we can do because of the equality relationship that we've developed. So by the associative property and the property of inverses, what we can do, we can assume that this plus this will, because this is the inverse of x, these will be the equivalent of 0, and similarly for this. And from the axiom A3, the existence of an identity and the existence of the inverses, we're able to say y is equal to z. Let me do one more example before we go on. It's a very commonly understood statement that x plus y is equal to x, then y will equal 0. So to be able to say something like this, we have to first, because we have the additional additive identity, what we can do is x plus y is equal to x plus 0, because if it's an identity, adding it will not change the structure of the equation. Then, similarly here, what we did in our last example, if we add the inverses, so if we add negative x, and we add negative x, and I can add it wherever I want in the formula because of the commutativity of addition, what we can do is we can cancel out our x's, and we're left with y is equal to 0. Simply subtracting x from x does not give us a construct of 0 unless we physically put a 0 there, which is commonly understood when we actually do our regular addition and subtraction. Okay. Now for today's real analysis lesson, I wanted to go over ordered sets. And an ordered set is simply a non-empty set S with a binary relation which is either the less than, the equal to, or the greater than, defined on all products of the set. So when I say a set's product with itself, I'm constructing an ordered pair, AB, that exists in our product, where we can manipulate AB in some kind of arrangement of this binary relation. So either A is less than B, A is equal to B, or A is greater than B. So, and furthermore, it will satisfy transitivity, which says that if A is less than B and B is less than C, then A is also less than C, and so on for all of these different relationships. If I'm saying that I have a subset of this set, I assume that there is an upper bound for the set K if there is an element U such that for every element in K, X, for every X existing in K, this element is greater than or equal to U, or U is greater than or equal to every element in X. K is called bounded above if there exists any sort of upper bound like this, where there is an element that is greater than every element in the set K. It is bounded below if there is an element that exists that is less than or equal to. So upper, I'll use L for the lower bound. There exists a lower bound for every element in X. Notice that for every upper bound of K, if there exists an element V such that U is greater than V, then by the transitive property of ordered sets, X is also, or not less than or equal to, but X is also bounded above by V. This idea of bounded sets is very important in analysis, and it's kind of the basis of both how we're going to think about numbers and real numbers and rational numbers, as well as how calculus itself is fundamentally understood. So it's very important. So to get a more intuitive idea, let's say I have a set. This line here represents my set S. Okay? I have a subset of this. Let's make it closed subset. So this point is included and this point is included in my cut of set S. That is my K. So any upper bound for my set K is anything that is less than or equal to, greater than or equal to all my elements of K. So if all my elements of K are symbolized by X, and let's say this point is U, then all X is less than or equal to U, or in this case, just greater than, or in this case, U is just greater than all elements in X. Now that we've talked briefly about what an upper bound is, which is a very generalized topic and kind of, it can be several different numbers, let's go into what a least upper bound is. So a least upper bound is an element that it is smaller than any other upper bound. So, as the definition suggests, it's the least of any of the upper bounds. So, L is an upper bound. L is an upper bound for K and for any other upper bound U, L is greater than or equal to U. So equivalently, if L is an upper bound for K and X is less than L, L is not an upper bound for K as well. A set which is bounded above may or may not have a least upper bound depending on the construction of your set itself. So we'll go into that further. So not every set will have an upper bound, but will not have a least upper bound, but it could still have upper bounds. So you might have upper bounds, but you might not have a least upper bound. So let's find an example of a least upper bound. So we've constructed here a set K such that K is equal to all X in Q that is between 0, that is greater than 0 or less than 1. So to prove that 1 is our upper bound, indeed what we have to do is we'll prove it by contradiction. What we're going to do is if it is not the upper bound of our set, then that means there is some other U that is less than 1, okay, that is X is greater than U, is greater than 1. But if U is any number that is less than 1, and we can see from the definition that if U is less than 1, that then there must be existing some X in our set that is between here and here. So that must mean that there must be U that is less than some X that is less than some 1. Because we assumed here that U is our smallest, our least upper bound. Because we're assuming for our contradiction that 1 is not our least upper bound. Okay? So we kind of forced in an X naught kind of a number that is less than 1 but greater than our upper bound. But that doesn't make any sense because our upper bound by definition is supposed to be by definition, if you remember, that X is less than all of our upper bound. So if 1 wasn't our upper bound, that means there must be some upper bound that is less than 1, and if that is the case, then there must be if U is less than 1, there must be some X that is also less than 1 in front of U. And that gives us our contradiction, because by definition our least upper bound is supposed to be greater than all of our X. Therefore 1 must be our upper bound, or our least upper bound. Notice for this example, our least upper bound proof shows that 1 is in fact not in our set, because by definition we constructed a set where 1 is greater than and not equal to X. But we could have similarly constructed a set where X is less than or equal to all 1, and we would have provided an upper bound, that least upper bound that is in our set and is greater than all the other points in our set. So that's okay as well. Now that we have a general idea of what a least upper bound is, let's make a general statement about all the least upper bounds of sets in n being the natural numbers. So every non-empty set K of n, which is bounded above, has a least upper bound. Now this is a pretty strong statement. I'm saying that if I take any set of natural numbers, and remember from last video, we created a natural number set which follows all of our 5 axioms by constructing with these points and arrows, right? We have the the element 1, we have the successor function, and so on. Now I'm saying that if I take any subset of these elements in the natural numbers, I am going to have a least upper bound. So suppose K is a non-empty subset of N. Okay, so non-empty subset of N. And we can clearly see that there are points which bound it above. So there are points greater than all the points in K. Now, let U be the collection of all upper bounds in K. So U is equal to upper bounds in, well, upper bounds of K, if this is our set K. Then we know U is non-empty because clearly here we have upper bounds for the set. And we also know that every non-empty subset of N has a smallest element. This we get from our axioms of natural numbers that we went over in the last video. If you remember, to recall, here are the 5 axioms of natural numbers. So our first axiom for natural numbers is that we have a set T, it's non-empty, and it contains an element, we'll call it 1. There exists a function within the domain of T whose range is also contained in T, so that for every A in T, S of A exists in T. Then third, for any AB that exists in T, if SA is equal to SB, so the successor function of A is equal to the successor function of B, then A is also equal to B. For any A in T, their successor function of A cannot equal 1. And then fifth, which is our most important axiom, if K is any subset contained in T and contains 1, and if A is in T, then S of A exists in K, ergo, the set K is equal to T. Ergo, K is equal to the natural numbers, all the natural numbers. So what that helps us understand is that for every non-empty subset of N, there must be a smallest element. If that last statement is indeed the case, then let's suppose that L is our smallest element of the set U. So there exists an L that is less than or equal to all U. Okay? And this upside down A just means all in set terminology. Since it's in U, it is an upper bound for K. So it's an upper bound for K. And it has been chosen so that for every upper bound U, L must be less than or equal to all the upper bounds of K. Ergo, there must exist a least upper bound. And this is simply from it's a consequence of the final axiom satisfied by N. Indeed, suppose U is in any non-empty subset of N and assume that U has no smallest element. So let's say that this is not the case. If this was not the case, right, then we'll prove that this is true by proving that if it's not true, we get a contradiction. Okay, so let's prove our least upper bound through a contradiction proof, which is one of the best ways of proving things in analysis and one of the most common ways you'll see proofs in analysis. So let T equal N in N. So that's the natural number is N. Okay. And we want N less than A for every A in U. Okay? So that assumes that the number 1 exists in T. Because if it's not, then 1 is in U itself, since it's clearly less than every other element of U from the axioms, because it's our starting element. Okay, and that would contradict the assumption that U has no smallest element. So 1 must be in our set. Now suppose N is in T. Or a better way to write this would be, suppose N exists in T. Then its successor, S of N, is also in T. Right? That we get from our fifth axiom. So if it's not there, there would be an A in U with A less than or equal to S of N. And we cannot have A less than S of N because N is the immediate predecessor of S of N. And that would have, which would contradict our assumption about N being in T. So we must then have an A equal to S of N. That is, we would have an S of N in U. Okay, so in our upper bounds. See, but that forces S of N that forces S of N less than or equal to U for all U existing in U, contradicting our assumption that U does not have a smallest element. Consequently, we have established that if N is in T, right, if we have an N in T, then a successor must also be in T. The final axiom for the natural numbers then forces our original value T to equal N, okay, to equal, so our original set T is the same thing as the entire set of natural numbers, and that would contradict the condition that U is empty. From this, essentially what we've done is we've contradicted that there cannot exist a least upper bound, because if there did not exist a least upper bound, then our original set would just be the same thing as our natural numbers, and there would be no such thing as an upper bound. So our axiomatic definition for the natural numbers provides that there must exist a least upper bound for any subset of the natural numbers. Okay? So let's talk about the rational numbers. And while in the future, we're going to show whether or not the real numbers, so that set of numbers that includes the rational numbers and the irrational numbers, we're going to go and check whether that has a least upper bound. But because we haven't defined the real numbers axiomatically or constructed it, let's start with the rational numbers. So for the rational numbers, let's take the set S, where X is, the elements X are in Q, and such that X squared is less than 2. And we're going to show that in this specific constructed set, we do not have a least upper bound. Okay, so we know that S is non-empty because if it's in Q, then it must have 0 and 1 within it. S is clearly also bounded above because we define it through using an ordering relation. Okay, so there must exist a set of numbers that are greater than all the elements in the set that we have. So to be bounded, remember, it's defined as there exists number m such that the size of any element in the set is less than that m, right? So we can clearly see that in this case, the number 2, because it's not included in the set, must be greater than any sort of x squared, where x is in the rationals, within our set, okay? But because we're talking about rationals, there exists no rational number that when squared is going to equal exactly 2. Therefore, there cannot exist a lowest number of rational number that you can give that is less than, or sorry, greater than all of the numbers in the set and is the least upper bound, because you will always find an upper bound that is smaller than your original number. So if we assume that S does have a least upper bound, just for an experimentation thought, a least upper bound for this set x squared must be somewhere between 1 and 2. So we know that a least upper bound L must be less than or equal to 2, if we assume that there exists a least upper bound, okay? And since 11 over 10 and like approximately numbers greater than 1 clearly exist in this set, we can just, for the purpose of argument's sake, say that 1 is greater than or equal to any L. So if there did exist a least upper bound, it would probably be somewhere between 1 and 2. And this is very important for our argument and how we're going to contradict the idea that there exists a least upper bound. So going back to the contradiction idea, we're going to contradict the statement that it exists to prove that it doesn't exist. So to contradict that there exists a least upper bound, we have to say that there exists some L squared is less than 2 is false. Then we have to show that there's some L squared greater than 2, and we have to show that this is false. So we know that in Q, L squared equals 2 is going to be false, because it then follows, so if we show that all of this is true, then it will then follow that no least upper bound exists. Because if there did exist a least upper bound within our set, then this statement could necessarily be true. This statement could necessarily be true as well, because then there would exist a point greater than all the values within our set, right, greater than 2, where we have a true statement, right? And similarly, the contrapositive of that exact thing. Okay, so let's do that and show that for our set, we have no least upper bound. And remember, we're looking for a least upper bound that is somewhere between 1 and 2, which doesn't exist. So suppose L squared less than 2 is true. So that means we can construct an element of S where L is less than S that contradicts L being an upper bound. The idea is to find a small rational number, let's go with 1 over n, for some integer n, such that S equal to L plus 1 over n is still existing in our original set S, which was the x squared is less than 2, okay? So if this is true, if we want this to happen, that would necessarily be the equivalent of saying L plus 1 over n squared is less than 2. If this exists in S, then this statement must be true. 1 over n is less than, so L squared plus 2L over n plus 1 over n squared is less than 2. And now because our L was between 1 and 2, right? It suffices to say that we need to find an n, right, here, where L squared plus 4 over n plus 1 over n squared is less than 2. So because it has to be less than 2, if we just multiplied it by 4, it'd be essentially doing the same thing, just slightly simplifying our problem here. So because it's between 1, the number 1, and 2, what I'm going to do is I'm going to substitute a 2 for L and make it a 4 over n. And this is totally okay because we know that if we have to find something less than 2 and greater than 1, if we just put it in as 2, it'd be totally okay. It just has to be less than, right? Since n is greater than or equal to 1, it's sufficient to have L squared plus 4 over n plus 1 over n less than 2. Because if it's going to be greater than 1, increasing the n isn't going to make our problem bigger, and therefore we will still have a number less than 2. Because as long as it's greater than 1, we're not going to make our number bigger. Right? So, because n must be greater than or equal to 1. Okay? So with that logic, I've taken out the exponent. Now, because I've taken out the exponent, wouldn't that just simplify down to 5 over n less than 2? We have to find some n or L that solves this function less than 2. So this would be the equivalent of 5 over n is less than 2 minus L squared because of I just subtract from both sides an L squared. What if I divided both sides by 5? Then I'd be left with 1 over n is less than 2 minus L squared over 5. Now by assumption, the right-hand side is given a positive rational number, i.e. a quotient of natural numbers. Remember, it was m over n to construct any rational number. That would be the form. Is it true that for every natural number quotient, AB, there is a natural number n where 1 over n is less than a over b. Well, of course it's true. We need some n that is greater than b over a, and since a is greater than 1, in this case, because our number was between 1 and 2, right? Any n greater than b will suffice, right? Because for any a, if we want a to be greater than 1, we have 5 here, so we don't have to worry about it. And then we need an n that's greater than b. Well, tracing back our steps, we have now found a rational number s that is bigger than L, which is still an S, and hence derived the contradiction that L squared is less than 2. Now let's suppose L squared is greater than 2. We will derive a contradiction for this. So we'll be doing this by contradicting an upper bound of u of s. So there exists a u which is less than L, and we'll contradict that L is the least upper, would use this to contradict that L is the least upper bound for our s. This time we will find a small rational number, 1 over m, for some integer m, such that u is the equivalent of 1 minus, or is the equivalent of L minus 1 over m, such that u is still an upper bound for s. This means we want some u in the set S where 1 minus 1 over m, L minus 1 over m squared is less than 2. This would then, if we expand our polynomial, this expands to L squared minus 2L over m plus 1 over m squared would be greater than 2. So we've expanded our polynomial, and because we're looking for a number that's greater than 2, it suffices to say that this small addition, 1 over m squared, or this very large addition, 1 over m squared, rather, we don't really need it, because we know that we're going, if there exists one, it's going to approximately be greater than 2. Equivalently, it's enough to have L squared minus 2 is greater than 2L over m. And since we already know that L is less than 2, it suffices to find m with L squared minus 2 is greater than 4 over m. So substituting the L for 2 so that we have 4 over m greater than L squared minus 2. So with that, we can divide both sides by 4 again. 1 over m is less than L squared minus 2 over 4, right? And again, L squared minus 2 over 4 is a fixed positive rational number, and the argument guarantees the existence of an m, because that's how we constructed our problem. So if that's the case, then this is a rational number smaller than L, which is still an upper bound for S, and hence derived the contradiction that L squared is greater than 2. because if such a rational number does exist, which it does, that would mean that there must be some number that when you subtract it from L, right, L minus 1 over m, you're still an upper bound contained in our set S. And if you're still contained in our set S, well then this ain't the least upper bound, is it? Because if it was the least upper bound, then you wouldn't be able to subtract from that least upper bound and still be contained within our S. Or, in other words, not contained in our S, but the condition that L squared is greater than 2 would not be true. And we can conclude, since L squared cannot equal 2, then there can be no such least upper bound. And to summarize one more time so that you fully understand where this argument is coming from, our least upper bound, well, least upper bound squared, cannot be less than 2. Our least upper bound squared cannot be greater than 2. And our least upper bound squared can very easily be seen not equal to 2. And remember, we're working in Q, the rationals. Then that follows that there exists no least upper bound. And we're not proving necessarily that this statement is false or this inequality is false. That's not, it's misleading to put the inequalities, but that's not exactly what we're doing. We're not disproving inequalities. We're making contradictions by forcing small rational numbers in between here, which prove that there exists a number that if you add it to this, you will still be contained in the same set. And there's a number that when you subtract it from this, a rational number, mind that, you will still be greater than 2. Okay, and that number was when we added a plus 1 over n to L, right, and we created the number S. And then when we subtracted a number 1 over m, let me just make a little line there. Subtracted number 1 over m to L, right? That number u. I cannot write today. To a number u. And therefore prove that if there exists a rational number that you can add to our L or subtract from our L, then obviously L isn't the least number or the greatest number, and therefore cannot be our least upper bound. And we know that intuitively because we know that the square root of 2 is a rational number, and that would technically be the upper bound for our system if we were using the real numbers. But in this situation, we're using the rational numbers, and the square root of 2 is not a rational number. And we cannot use this to say that it is a least upper bound for our rational number set, right? Because if it's not in the set, it cannot be a least upper bound for the set. So thus we have a differentiation for the n's and the q's in terms of the general properties of non-empty subsets that are bounded above. If K is a subset of n, then by the definition of the natural number axioms, there exists a least upper bound. But if K were a subset of Q, it may or may not have a least upper bound, as we have seen examples of both cases. And that, folks, wraps up today's lecture in real analysis. I hope you enjoyed. If you have questions, please leave them down in the comments below. And don't forget to leave a like and subscribe to my channel. Thank you.